Hey friends, welcome to the YouTube channel all about electronics. So some time back, we have seen the fixed bias and the self-bias configuration of the JFET. So in this video, we will learn about the voltage divider biasing configuration of the JFET. But before we go through it, let me just quickly revise why we need to bias the JFET and why we are studying all these different types of biasing configuration. And also we will understand why some configurations are more preferred over the other biasing configuration. So similar to the BJT, the JFET can also be used as an amplifier. And to use it as an amplifier, it needs to be biased in the active region, or in case of the JFET, it is also known as the saturation region. So in the earlier videos, we have seen that to bias the JFET in the active region, this VDS should be greater than or equal to VGS minus VP, where this VP is the pinch off voltage and the absolute value of this VGS should be less than VP. So this second condition ensures that the JFET does not go into the cutoff region, and by fulfilling this condition, the JFET can be biased in the active region. And in the active region also, it should be biased in such a way that we get the maximum voltage swing without any kind of distortion, and the biasing point should be as stable as possible. That means even if there is a variation in the device parameters, then also there should be a minimum effect on the biasing point. So for the JFET, there are three basic biasing configurations: the fixed bias, the self bias and the voltage divider bias. In case of the fixed bias configuration, the gate is biased with the fixed voltage. Let's say this blue curve is the ID versus VDS characteristic or the transfer characteristic of the JFET. And when the FET is biased with this fixed bias configuration, then this yellow line represents the load line. So here, this is IDSS and this point is the VP. Now typically for any JFET, this IDSS and the VP varies in the certain range. Let's say this blue curve shows the maximum value of the IDSS and the VP. And let's say this green curve shows the minimum value of this IDSS and the VP. So as you can see from this graph, because of the change in the IDSS and the VP, this is the maximum change in the drain current. So in case of the fixed bias configuration, because of the change in the device parameters, there is a significant change in the operating condition. And using the self-bias configuration, this change can be reduced. Because as we have seen in the earlier video, in case of the self-bias configuration, the voltage VGS is equal to minus ID times RS. And in the active region, this is the relationship between the drain current ID and the voltage VGS. So as the drain current ID tries to increase, then this voltage VGS will also increase. And from the second expression, as you can see, when the voltage VGS will increase, then this drain current ID will reduce. So because of this source resistor RS, there is an inherent feedback in this self-bias configuration. And because of that, it tries to stabilize the operating point. Now in case of this self-bias configuration, since VGS is equal to minus ID times RS, so the load line will pass through the origin. And in this case, because of the change in the device parameters, if we see the maximum change in the drain current, then it will be less than the fixed bias configuration. But further this variation can be reduced by using the voltage divider biasing configuration. Or in general terms, if we bias the JFET with the gate voltage along with this source resistor, then the stability can be further improved. But instead of using the two supply voltages, the JFET can be biased using the single supply if you bias it using the voltage divider biasing configuration. So first of all, using the graphical method, we will see that how we can find the operating point of the given circuit. And at the later part of the video, we will see that using the Shockley's equation, by solving the quadratic equation, we can also find the operating point. So for the DC analysis, all this coupling and the bypass capacitors will act as an open circuit. And this will be the equivalent circuit. Now for the JFET, this gate current IG is approximately equal to 0. That means approximately no current is flowing into this gate terminal. That means on the input side, the current is flowing through this resistor R1 and the R2. And hence we can say that this voltage Vg is equal to R2 divided by R1 plus R2 times VDD. That means using the voltage divider rule, we can find this gate voltage. Now if we apply the KVL in this loop, then we can say that voltage Vg minus VGS minus ID times RS, that is equal to 0. Because here the current which is flowing through the source terminal is equal to ID. Because in case of the JFET, this ID is equal to IS. So from this expression, we can say that voltage VGS is equal to Vg minus ID times RS. Now as per the Shockley's equation, in the active region or in the saturation region for the JFET, this drain current ID can be given as IDSS times 1 minus VGS divided by VP square. So as per this expression, let's say this is the transfer characteristic of the JFET. And using this expression, we can find the load line of the given circuit. So let's say when this drain current ID is equal to 0, at that time, this voltage VGS is equal to Vg. That means one point will be somewhere around here. Similarly, when this voltage VGS is equal to 0, at that time, this drain current ID is equal to Vg divided by Rs. So on this line, the VGS will be equal to 0. And somewhere around here, we will get the value of ID as Vg divided by Rs. So by joining these 2 points, we will get the load line. And if we further extend this load line, then at some point, it will intersect with the transfer curve. And the intersection point of this load line and the transfer curve will give us the operating point. That means this current is IDQ and this voltage is equal to VGSQ. Now let's consider the variation in this transfer curve. Let's say this blue curve shows the maximum value of the IDSS and the VP. And this green curve shows the minimum value of the IDSS and the VP. So if this is the maximum variation in the IDSS and the VP, then the variation in the drain current would be this much. And let's compare this variation with the self-bias configuration. So let's say for the self-bias configuration, this red line is the DC load line. And with that load line, the maximum possible variation in this drain current is equal to this much. So as you can see, in case of the voltage divider biasing configuration, the operating point will be more stable and it is more resistant to the change in the device parameters compared to the self-bias configuration. Now most of the time, the transfer curve of the JFET is not known to us. So in that case, using the Shockley's equation and solving the quadratic equation, it is possible to find the operating point. So let us see that. Now as we have seen, the voltage VGS can be given as Vg minus ID times Rs, where this Vg is equal to R2 divided by R1 plus R2 times VDD. Now by putting the value of this VGS in this Shockley's equation and solving this quadratic equation, we can find the value of the drain current. And by putting the value of this drain current, we can find the value of the VGS. And for the given circuit, the drain to source voltage VDS will be equal to voltage VDD minus ID times Rs plus RD. So in this way, by finding the drain current ID and the VDS, we can find the operating point. Alright, so let us take one example so that it will get clear to you. So in this example, the JFET is biased in the voltage divider biasing configuration, and for the given circuit, we have been asked to find the voltage VGS, current ID and the voltage VDS. So first of all, let us find this gate voltage. So this gate voltage Vg will be equal to R2 divided by R1 plus R2 times VDD. So in this case, it will be equal to 110 divided by 110 plus 910 times 20 volt. That is equal to 2.157 volt. Now if we apply the KVL in this loop, then we can say that voltage VGS is equal to VG minus ID times RS, right? That means VGS is equal to 2.157 minus ID times RS, and here RS is equal to 1.1 kilo ohm. That means we can say that VGS is equal to 2.157 minus ID times 1100. Now as per the Shockley's equation, this drain current ID is equal to IDSS times 1 minus VGS divided by VP whole square. So here this IDSS is equal to 10 milliampere, while the pinch off voltage VP is equal to minus 3.5 volt. That means this drain current ID is equal to 10 milliampere times 1 minus VGS divided by minus 3.5 whole square. Or we can say that this drain current ID is equal to 10 milliampere times 1 plus VGS divided by 3.5 volt whole square. Now in this expression, let us put the value of VGS, and as we have seen, this VGS is equal to 2.157 minus ID times 1100. That means drain current ID is equal to 10 milliampere times 1 plus 2.157 minus 1100 ID divided by 3.5 whole square. Or if we further simplify it, then this drain current ID is equal to 10 milliampere divided by 3.5 whole square times 3.5 plus 2.157 minus 1100 ID whole square. That is equal to 10 milliampere divided by 3.5 whole square times 5.657 minus 1100 ID whole square. So if we further simplify this expression, then this drain current ID will be equal to 2.61 times 10 to the power minus 2 minus 10.16 times ID plus 987.7 times ID square. Or from this we can say that 987.7 times ID square minus 11.16 times ID plus 2.61 times 10 to the power minus 2 is equal to 0. So in this way, we got the quadratic equation in terms of the current ID. And solving this expression, we will get the two roots of the drain current. And these two roots will be 3.3 milliampere and 8 milliampere. But the value of drain current as 8 milliampere is not possible, because with this value of drain current, if we find the value of VGS, that is VG minus ID times RS, then in this case it will be less than VP. And if that is the case, then the drain current ID should be equal to 0. That means for the given configuration, the value of the drain current ID is equal to 3.3 milliampere. And with this value, the voltage VGS is equal to 2.157 volt minus 1100 times 3.3 milliampere, which is equal to minus 1.47 volt. That means ID is equal to 3.3 milliampere, while the VGS is equal to minus 1.47 volt. And similarly, now let us find the value of the VDS. So this VDS will be equal to VDD minus ID times RD plus RS. So here the VDD is equal to 20 volt, while this ID is equal to 3.3 milliampere. This RD is equal to 2.2 kilo ohm, while the RS is equal to 1.1 kilo ohm. That means VDS will be equal to 9.1 volt. So in this way, we got the value of the drain current ID, the voltage VGS and the VDS. Now suppose if we reduce the value of the source resistor RS, then what will happen? Well, as we reduce the value of RS, then the drain current will increase, because as you can see from this expression, when the voltage VGS is equal to 0, that means on this horizontal line, this drain current ID will be equal to VG divided by RS. So as the value of this source resistor reduces, then the slope of this line will increase. And because of that, the intersection of this load line with the transfer curve will occur at the higher point. That means as we reduce the value of this RS, then the drain current ID will increase. So please find the drain current for the given circuit when we reduce the value of this RS to the half. So if you follow the same procedure, then you will be able to find that. And for the same circuit, also try to find the minimum value of this source resistor or RS minimum such that the circuit still operates in the active region. And do let me know your answer in the comments. And if possible, then I will also cover the similar type of question on the second channel. But I hope in this video, you understood the voltage divider biasing configuration of the JFET. So if you have any question or suggestions, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.